Are there any other questions today from anybody? Okay, then let's get started for today. And let's now move into the real core of what this class is all about. Transistor amplifier design. What are we going to use transistors for? Well, in this particular class, we're going to focus a great deal on a concept you guys are already familiar with. We used this triangle shape before to illustrate the operational amplifier, which you're all familiar with. So in this case, what we're going to do now is we're going to look inside that triangle. How do we build the circuits that cause a device or a component to act like an amplifier? And so in this case, when we mean an amplifier, we mean some type of time-varying signal like voice or music or video. And it comes in at a small amplitude, and we're going to put it through an amplifier, and it comes out at a much larger amplitude. We're going to increase the amplitude of the signal. So this type of amplification we're all very familiar with, and you've all looked, for example, in Circuits 1 at inverting and non-inverting amplifiers. So how do we make transistors, how do we use transistors to cause this type of behavior to happen? So what we're going to need to do is, since we're going to be dealing with AC signals, time-varying signals, we are going to need to analyze amplifier circuits in the small signal domain. So we're going to require small signal analysis. Which means if we're going to use BJTs and MOSFETs in these amplifier circuits, then for both MOSFETs and BJTs, we're going to need small signal models for both. So just as we did a small signal model for the diode, we're now going to do the small signal model for the transistor. Now, when we're designing amplifier circuits, the only regions of operation we typically care about for a MOSFET is going to be saturation. For a BJT will be forward active. So we're going to create small signal models that correspond to those operating conditions. And why do I care about saturation and forward active? Because as we recall, when we looked at either IC or ID, the collector current or the drain current, and we plotted that against VCE or VDS, in both curves for both the MOSFET and the BJT, we saw this type of behavior. Out in this region, as we pointed out before, both the MOSFET and the BJT behave like a current source. So this region for a MOSFET corresponds to saturation. This region for a BJT corresponds to the forward active region. So that's what's going to be our focus. There's really, for building amplifiers, we're not normally going to deal with the ohmic region in transistors or with the saturation region because those make terrible amplifier circuits. But we can make very good amplifier circuits out here. All right, so what's our analysis technique going to be? Well, we've already talked about this before. We're going to either calculate or choose a DC bias point. So I'm going to give you a transistor circuit, or you're going to design a transistor circuit, and you have to figure out what are the DC operating conditions for that circuit. What are the currents and what are the voltages? We're going to use DC equations for this. And in general, those DC equations are going to be nonlinear. The behavior of MOSFETs and transistors is nonlinear. It has squares and exponentials in it. Then the output of this will be our Q point, our quiescent point, our bias point. And then we're going to feed those bias point values into our small signal AC model. And as we talked about before, the idea behind a small signal AC model is that it is a linear approximation. So the Q points are used, or the DC values from the Q point are used to calculate the small signal parameters. And so that's part of the input to our small signal model. The other input will be our AC input signal. And then the output is going to be our AC output. So some kind of output voltage or current, for example, in the AC domain. So typically we're going to be looking at input voltages and output voltages. Vin and Vout are what we're typically going to work with, although of course you can also have small signal input and output currents as well. But most of the examples in the book deal with voltage. So we've seen this before. I sketched out this model before. We talked about small signal analysis with diodes. We're going to do exactly the same thing here. And once you're over here in this region, everything from this point on becomes 2112. Okay? This all becomes your Circuits 1 class. So it's material you've seen before. So you've got to be good and confident about doing nodal analysis. You also have to be confident about using Thevenin's theorem, because as we're going to see later on, that also becomes very critical when we analyze these circuits. Okay, this is what you're going to get really good at for the rest of this semester. And if you can master this, then you'll have no trouble at all, because the beauty of this is once you understand this technique, I can give you a circuit you've never seen before, and you can analyze it and figure out how it works. That's the whole purpose behind what we're trying to do in this class, is to have the tools, because without the tools you can't design. All right? So what we're going to do is we're going to first develop a small signal model, and then once we understand how to do it, we're going to look at what I would call building blocks of circuit design, building blocks of analog design. So you'll hear the word analog versus digital. Okay, so for digital circuits, everything's very simple. Everything's either a 0 or 1. It's all Boolean algebra. So voltage levels only represent 0 or 1. But for analog circuits like this, all of our signals, our voltages, are time varying over a wide range of values. So they're not simple discrete values. So everything we're going to focus on is what we call analog design, with time varying signals that don't have any particular value. All right, so let's start. And we're first going to start with MOSFETs. We're going to look at some basic amplifier circuits so we can build MOSFETs. And then once we understand those, we'll look at BJTs. Fortunately, very fortunately, although the DC equations are quite different for the MOSFETs and for BJTs, the small signal models are almost identical. With the exception of an additional resistor with the BJT, it's the same small signal model. So we're going to start with MOSFETs. We're going to learn how to do the analysis techniques, and then we'll go over and quickly cover BJTs. But once you understand MOSFETs, BJTs are very easy to understand too. So let's first talk about the small signal MOSFET model. So for our MOSFET, let me go ahead and sketch this out. Let's go ahead, and I'm going to start by developing a small signal model for an NFET, for an NMOS transistor. So in this case, I've got my drain, my source, my gate. I've got a drain current that flows into the drain. I've got a drain source voltage between the drain and the source. And I'm assuming in this case the source and the bulk are simply connected together. So I'm drawing it as a 3-terminal device. And then I've got a gate source voltage, VGS. And as we recall, in saturation, the drain current is a function of the gate source voltage and the drain source voltage, VGS and VDS. So when we looked at our DC equations, we had to solve for those. Although typically we would ignore lambda, so VDS didn't come into the equation, but it's in there as well if we look at the channel length modulation effect. Okay, so I want to take this same idea and I want to move this over to the AC domain. I'm going to want a small signal model that describes the effect of the drain current due to both the drain source and the gate source voltage. So I want to look at the partial derivative of the drain current with respect to VGS and the partial derivative of the drain current with respect to VDS. And that's going to allow us to create a comprehensive small signal model. All right, so once again, we're focusing on saturation. So we're going to use strictly the saturation equations. That is our desired region of operation. So let's go ahead and let's write ID sat. So our drain current equation in saturation, as we all know, is going to be K prime N over 2 times W over L times VGS minus VT squared times 1 plus lambda VDS. So we're all familiar with that equation. We've seen it before. Let's take that equation and let's do a derivative with respect to VGS. And I want to evaluate that derivative at some Q point. So we're going to assume we are at some DC bias point in terms of the values we're going to get. So in this case, if we take this derivative, this will be equal to K prime N over 2 times W over L times VGSQ minus VT times 1 plus lambda times VDSQ. That's the derivative we get. And we give a name to this. We say this value I just got is G sub M. We call that the MOSFET transconductance. So we're going to make an approximation. Yes? With VGS squared times 2. K, oh, I'm sorry. Pardon me. That's K prime N. Thank you very much. I'm sorry. That's K prime N. Thank you. Okay. All right. K prime N W over L. Thank you. Okay. So here's our MOSFET transconductance equation. All right. So I'm going to now make an approximation we've made before. If lambda VDS is much less than 1, in other words, if this is small compared to 1, then the transconductance will approximately be equal to K prime N W over L times VGSQ minus V sub t. So just as I did before, I'm ignoring that lambda because it's small compared to 1. It only causes a few % error. It makes my math a little bit easier. All right? Here's our equation for transconductance, and we're going to see how we're going to use that in just a minute. Now, there is an alternate expression. Let's look at another way to look at transconductance. Let's let IDQ, my quiescent drain current, be equal to K prime N over 2 times W over L times VGSQ minus VT squared. So I'm just going to write this. Once again, I'm ignoring lambda, just as I did before. And if I do that, I'm going to do a little bit of math. I'm going to divide by these terms, and then I'm going to take the square root. So in this case, VGSQ minus VT will be equal to the square root of 2 times IDQ times L over W times 1 over K prime N. So taking this, I've got VGSQ minus VT. I'm going to take this, and I'm going to substitute that into here for the VGSQ minus VT. Let's substitute into our GM equation, and then what we're going to get is that GM is equal to K prime N W over L times the square root of 2 times IDQ times L over W times 1 over K prime N. So all I've done is I've simply taken that VGSQ minus VT and then just take that and plug that into that equation we had before. Once I've done that, I'm going to take this W over L and this K prime N, and I'm going to factor them into this equation. So in this case, what I'm going to get is if I take this now and simplify this, what I'm going to get is that simplifying, GM will be equal to the square root of 2 times K prime N times W over L times IDQ. And here is another equation for GM. Mathematically equivalent. What's the difference between these two equations? This equation tells me GM in terms of the gate source DC bias voltage. This equation tells me GM in terms of the bias drain current. So depending upon which of those two DC values you have, you can use either one of these equations. You'll get the same answer. They're mathematically equivalent. All right, so there is a third equation we can use for GM, which once again relies upon us combining terms together. Let's see. We can also write GM this way. let's take that original equation and let's multiply top and bottom. Let's just turn this into a fraction, and I'm just going to multiply by square and then have VGSQ minus VT in the denominator. And why did I do this? Because in this case, what is K prime W over L VGSQ minus VT? Well, isn't this part here just equal to 2 times IDQ? So I don't have the K prime N over 2. I've got just K prime N. So that's equal to twice times the drain current for that top equation, divided by VGSQ minus VT. And here's GM. Now this is a handy equation. Why is this equation useful? 2 IDQ divided by GSQ minus VT.
It's independent of your transistor.
Well, it's not that it's independent, but you don't need to know the transistor parameters.
Right.
Exactly. So in other words, for these equations, you have to know K prime N and W over L. But if you just know the quiescent drain current and the quiescent gate source voltage, you've got the transconductance. You don't need to know K prime N and W over L. So this is a way of actually deriving the transconductance directly from your DC measurements. All right, so these are all, like I said, mathematically equivalent. You can use all of them or any of them, okay? But this one in particular is sometimes very handy, okay? But these others, one of the most common equations we will use in this class will be this one because it's easy to calculate ID. All right? Now, in addition to this, I also want to calculate the change in the drain current with respect to VDS. And as we recall, we mentioned this before, ideally, the curve for ID versus VDS is completely flat in saturation. But what we realized, or we talked about before, is because of the channel length modulation parameter, the actual curve increases slightly. Well, that behavior we want to capture, which is why we care about this delta ID over VDS, probably the partial derivative of ID with respect to VDS. So therefore, I want to define another term. All right, now let's define this. Let's define G sub O, which is the drain source output conductance. So we want to capture this behavior, this non-ideal behavior. So of course this comes down to the partial derivative of drain current with respect to VDS at some Q point. And once again, if we start with our original drain current equation, we're going to get lambda times K prime N over 2 times W over L times VGS minus VT squared. So from this derivative, we note that once again, this quantity here is approximately equal to IDQ. Again, there's no 1 plus lambda on the end, so it's a slight error, but it's close enough, which means I can now write the output conductance as being equal to lambda times IDQ. So that is my drain source conductance. We did something similar for this for the triode region, for the ohmic region before. We did something similar, but now we're doing this in saturation. We therefore define R sub O as our drain source output resistance. Which is going to be nothing more than the inverse of the conductance. And therefore, it's equal to 1 over lambda times I dq. All right? Now, this was all for NFETs. For PFETs, we're going to find that the transconductance gives us basically a very similar equation. For a PFET, GM will be equal to K prime P times W over L times the absolute magnitude of VGSQ minus VT, because of course those are going to be negative numbers. We can't have a negative transconductance, so we take the absolute value. Or that's equal to the square root of K prime P, 2 times K prime P W over L times I dq. In this case, the equation is the same because the drain current is always positive. It's just flowing in the opposite direction, going from source to drain instead of from drain to source. So we have very similar G sub M equations. R sub O will be equal to 1 over the absolute magnitude of lambda times I dq because, again, lambda is a negative number. Well, we want positive numbers. You can't have negative transconductances. You can't have negative resistances in the model. So for the PFET, we take the absolute values. All right? Questions about this? And once again, you'll have all these equations in front of you. So you don't need to memorize any of these. You'll be able to they'll be right on the data sheet. But obviously, you need to be able to use them. Yeah?
So in the alternative forms for the transconductance, do we just ignore lambda entirely?
Well, generally, you're going to use these formulas for the transconductance, and we're not going to worry about lambda because having lambda in the transconductance formula only causes a couple of % of error. And so we deliberately ignore it to make the math easier, although actually it is there. But again, for the model, for within a couple of % error, it's fine. We don't worry about it. But for R sub O, it's clearly a dominant term. We can't ignore lambda there because it's lambda multiplied times this term here. So lambda has to stay in the R sub O. Can't get rid of that. But yes, just as we've seen before, we are dropping the lambda when it is 1 plus lambda because then it's going to be a small quantity. It makes the math easier. All right. Now, I also want to point out something else the book does, which other textbooks don't, but our book does. Our book defines VA equal to 1 over lambda for a MOSFET. Where does this come from? Well, this comes from BJTs. Remember, for BJTs, we had a 1 plus VCE over VA term, where VA was the early voltage. And for MOSFETs, we started off by defining 1 plus lambda times VDS, where lambda was channel length modulation. Well, obviously this has units of volts. That has to have units of inverse volts. Well, the authors of the textbook, once again, they don't like the collector, the BJT and the MOSFET's equations to be different. And so they go ahead and say, hey, let's just go ahead and define the MOSFETs the same way we define the BJTs. Let's call this 1 plus VDS over VA. Let's define the same form. So V sub A is typically considered the early voltage. Except the early voltage is a phenomenon that applies to the PN junction of a BJT. The early voltage is not the same thing as the channel length modulation parameter. It's a different physical mechanism. But the book wants the equations to look the same. Other textbooks don't make that distinction. They just use lambda for MOSFETs, okay? So I just want to point out, the book does this. It'll give you a VA value for a MOSFET, which really, it's not really an early voltage like you'd think for a BJT. But it has the same function. It's nothing more than the inverse of lambda. So just I want to warn you guys about that. On the exams, I don't try to do that. I just give you the lambda equation, which was the original one. But once again, the authors, they have certain ways they want to try to present material. They don't want to have negative signs. They want the equations to look as similar as they possibly can, and so they do this. Just want to give you a heads up. All right? So we've gone through and we've derived our equations. Well, what does our model look like? Okay. Let's go ahead and let's draw our small signal model. Keep in mind, the behavior we're trying to capture with our model is when the MOSFET behaves like a current source. And not surprisingly, that's exactly what our small signal model is going to look like. Here's our small signal model for our MOSFET. Gate, drain, source, and bulk terminal. And here are the two elements that I'm going to plug those two small signal parameters, equations I just derived. So in this case, this is GM times VGS, the AC value of VGS. And the AC value, the voltage between the gate and the source, that VGS plugs into this. So keep in mind, these are AC voltages we're talking about, VGS. So there's our GM term. That GM term tells us we've got a dependent current source, a voltage-controlled current source, which describes the behavior we see for that current source behavior in the saturation region. And then that non-ideal behavior, we have the extra current between the drain and the source, that resistor models that. So as we make VDS larger, additional current flows through that resistor. And that gives us that non-ideal slope. In its simplest form, that's it, guys. That's the small signal model, two elements. All right? Now, this, of course, was for the INFET. What is the PFET small signal model going to look like? Anybody want to venture a guess? Okay. What? Well, DC current's flipped. Is there a DC current in this diagram? No? That's a trick question I just asked you guys. Okay, I don't normally ask trick questions on exams, but I will do it during lecture. Okay? That's a trick question. These are AC voltages. There's no polarity to them, right? So it turns out the small signal model for a PFET is exactly the same as for the INFET. In both cases, increasing the small signal AC voltage between the gain and the source increases the small signal current, AC current flowing between the drain and the source. So AC is not DC. Also, And I want to emphasize, this is only valid in saturation. We use the saturation equations to derive those parameters, those model parameters, so it is only valid in saturation. But that's really where we want to use the transistor. Transistors that aren't biased in saturation, MOSFETs, are not very good amplifiers. They're terrible. All right? So, what are we going to do here? We're going to do the same kind of thing we've talked about before. We're going to solve for our DC equations. Then we're going to draw a small signal equivalent circuit and then solve for our AC parameters. So we did this with the diode circuit. Let's now do the same thing with a MOSFET circuit. And let's start with a very simple example. Okay, here's our first amplifier circuit using a transistor. Okay, now you're moving into real electronics. This is what we did. This is what people wanted transistors for when they first invented them, to do something like this. MOSFET connected with a resistance between the drain and the power supply. I've got an input which is composed of a DC voltage, that's to set our bias point, plus an AC V sub S, small signal input voltage. And I'm going to have a small signal output voltage at the drain, which when you think about it, it's the only place that makes sense. There's no other node available that has any kind of possible output, but at the drain of the transistor. Okay, so given this, let's assume that K prime N is equal to 50 microamps per volt squared. V sub T is 1 volt. W over L is equal to 10. And lambda is equal to 0.01 inverse volts. And since this is an amplifier, I want to find the amplification factor. I want to compute AV, which is equal to VO over VS, where AV is my small signal AC gain. And of course, gain, amplification factor. We've heard that before. We've been using that since circuits 1. So let's compute this. And to do this, we're going to have to first calculate the bias point, then go through and convert to the small signal model, and then calculate the AC values. All right, so let's take that circuit. So first of all, let's solve for the DC bias point. So when we do this, we ignore the AC sources. So think of this as superposition. I only want to solve for the DC value so that Vs goes to 0. I ignore it. All right, so is the transistor on? Let's ask that question first. Is it on? Yeah, it's definitely on because 2 volts is greater than the threshold voltage. So definitely the transistor's on. Well, if it's on, let's assume it's saturated. If we assume saturation, then ID is equal to K prime N over 2 times W over L times VGS minus VT squared. And once again, notice in my DC equations, I ignore lambda. I'm doing that to make things easier because ignoring it simplifies my math. It only causes a slight error in my DC values. So as always, unless I tell you otherwise, for DC calculations, we can ignore the effect of lambda. That's usually a good idea, unless I tell you to do otherwise. Or unless a problem tells you to do otherwise. Okay? So, I'm ignoring lambda. I can now plug in the values. This is easy. And therefore, I get that ID is equal to 250 microamps. That's my drain current. What is the drain voltage? So in this case, I want to know the DC drain voltage at that drain. VD is therefore equal to 5 minus 10,000 times ID. Plug this in, and I get that this is equal to 2.5 volts. Is this transistor in saturation? Okay. Is VDS greater than VGS minus VT? Or is VD greater than VG minus VT? Yes, So in this case, VD is certainly greater than VG minus VT. 2.5 is greater than 2 minus 1. And therefore, saturation is confirmed. So once again, I check the boundary condition just to make sure I'm actually in saturation. So, I also want to point this out, guys. I'm never going to try to trick you on an exam, but obviously if somebody else gives you a circuit, you've got to confirm that the circuit actually was designed properly. Maybe that person specified the wrong resistor value. Maybe you made a mistake, whatever. But you have to check, you have to confirm that it actually is behaving the way you want. So it's in saturation, so I know it's in the proper region. All right? Let's now go and let's convert to the small signal domain. So let's now do our small signal analysis for part 2. I'm going to put back in my AC voltage, and I'm going to zero out my DC voltages. So I set my DC voltages, my voltage sources, they go to 0. If I have a current source, that goes to 0, becomes an open circuit, right? So now I have VS. That's connected to my gate. Now I'm just going to take that model, and I'm going to take that circuit, and I'm going to plug it in here. My source and bulk terminal is just grounded. R sub O is also grounded on the other end since the source is grounded. So here's my R sub O. So VGS, the small signal voltage, is what appears between the gate and the source, which is just ground. So VGS will appear. And over here at the drain, I've got a 10K resistor that's connected from the drain to a 5-volt DC source, but the 5-volt source is now 0. It's ground. And so I'm going to add that resistor. So here is my transistor model. And I plug that in, and then I add the external components to it. And there's my small signal diagram. If there's one place where I see students make mistakes when they work these kinds of problems, it's from going to here to here. Taking the DC model and then drawing the small signal equivalent. Even when they have that sitting in front of them, I see time and again people will make mistakes. And they'll make an error in drawing the small signal model. You've got to be careful about that. Because if you draw the incorrect small signal model, you're doomed. You're certainly not going to get the correct answer. All right? Okay, so here's our small signal model. Now we need to include this as well. This is GM times VGS for the value for that small signal source. Okay, so now, what do we need to do now? Now I need to go through and calculate the parameters. GM and R sub O. Well, where am I going to get those from? Back here. What's ID? My quiescent drain current, IDQ, was just 250 microamps. So I'm going to plug this into my equations for GM and for R sub O. And so in this case, G sub M will be equal to the square root of 2 times K prime N times W over L times IDQ. I'm just going to use the current form equation, plug in the parameters up there, plug in 250 microamps, and what I get is this is equal to 500 micromos. Okay, if you're a guy like me who got started back before we adopted Siemens as the official unit of conductance, or 500 microsiemens. For my R sub O is equal to 1 over lambda times IDQ. Again, lambda is given. Here's where I need to use it. Plug into IDQ, and I calculate it, and what I will get is this is equal to 400 kilo ohms. So here's where I need those DC values, because I need them to calculate the values of the small signal parameters in the model. Okay? With these values, what I do now? A little bit of nodal analysis. 2112. All right. Well, by inspection, VGS is just equal to our signal source, V sub S. Same voltage, obviously. All right. We do a KCL. The only place I can write a KCL equation is at that drain node. Let's do that. So the KCL at the drain, I'm just going to define these currents like this. Now keep in mind, I'm defining the small signal V sub O voltage at the drain node. And so therefore, I'm going to write everything in terms of that V sub O. So for my KCL, I've got that GM times, in this case, VGS plus V sub O over 400K plus V sub O over 10K is equal to 0. Which of these terms is going to dominate, by the way? The 10K resistor, right? 10K in parallel with 400K, clearly that 10K resistor is going to dominate the equation. And so in this case, if I go through, I'm going to substitute for GM VGS. I'm going to say this is equal to GM times VS. And now I'm just going to rewrite this equation. And therefore, what I'm going to get is that VO over 9756 is equal to minus 500 times 10 to the minus 6 times VS. So that's my 10K in parallel with 400K. It becomes 9,756 ohms. And therefore, VO over VS will therefore be equal to minus 4.88. Do I have an amplifier? Yes, I do. What's the magnitude of the output voltage over the input voltage, V over Vs? Well, it's 4.88. But I've got a negative sign here. What does a negative sign mean? Well, we've seen this. What did a negative sign mean when we looked at op amps back in circuits 1? It's an inverting amplifier. What does that say about the phase of the input and the output voltage? They're out of phase with each other. So in this case, what you're going to see is something like this. So in this case, if you've got Vs with respect to time, and you've got a small input voltage, my output voltage is going to be larger, but it's going to be 180 degrees out of phase. So that negative sign indicates 180 degrees out of phase. In other words, it's an inverting amplifier. We've seen this before. You've all seen this before. You talked about inverting amplifiers with op amps, except now we're doing it with a single transistor. Okay. What I just did is what you're all going to have to get really good at before the semester's over. If you can do what I just did with more complex circuits, then you will have no trouble at all making an A in this class, because this is the essence of what this course is all about. Being able to do this analysis. And once you can do the analysis, then you have the tools to start learning how to design circuits. You can't design unless you can analyze. So this is the first step. So obviously, gain matters a great deal. Clearly, you're building an amplifier. You want to know what V out over Vn is going to be. How much amplification, how much gain you get out of it. But it turns out there are other parameters we care about in an amplifier besides gain. Okay. Actually, let me redraw that circuit. Shouldn't have erased that. Let me do this instead. Let's draw it over here. So I'm going to draw it a little bit differently here. Let's take this ground terminal, and I'm going to extend this ground terminal a little bit. Okay, so clearly we care about the output voltage versus the input voltage. We care about gain. But there are two other parameters that are important, and those parameters are the input and the output resistance of the amplifier. Ri and Ro, what are those? Ri is the AC input resistance of the amplifier. Or when I say AC, I mean the small signal. R sub O is the AC or small signal output resistance of the amplifier. Well, how do I represent these on this graph? Well, there's a reason why I extended this out. R sub I is the effective resistance here looking into the input of that amplifier circuit. R sub O is the effective resistance seen looking into the output terminal with respect to ground. And typically we're going to define the input and output resistance with respect to the ground terminal. Now there's an alternate notation you guys will also see that's in the book. Sometimes you'll see it represented this way. They'll do this right angle arrow looking into the output terminal. What they mean is that's the output resistance of this terminal with respect to ground. Or you'll see it drawn this way. R sub I. What is the input resistance looking into the input with respect to ground? So you'll see that alternate notation that's also used in the text, and in fact a lot of textbooks. So in this case, it's implicitly understood this is being done with respect to ground, so you don't have to draw that ground terminal. You don't have to stretch it out that way. Okay, well, what are the input and output resistances? Well, let's go ahead and let's do that. Let's redraw our circuit that we just had a minute ago. So in this case, what I want to know what's R sub I looking into the gate, because the gate terminal is the input of the transistor. And what's R sub O looking into the drain, because the drain terminal is the output of the amplifier circuit. Okay? So I want to know the input and output resistance, the equivalent input and output resistances between these nodes and ground. Boy, that sounds awfully familiar, doesn't it? Remember back to 2112? How do we find the equivalent resistance between two nodes in a circuit? What technique do we use? Thevenin's theorem, absolutely. Okay, guys, here's where Thevenin's theorem kicks in. This is where you're going to be using Thevenin's theorem for the rest of this semester. Because you need to be able to calculate the input and output equivalent resistances of circuits. And I'm going to show you shortly why that is so incredibly important to us. Okay? So let's go and let's calculate those for this circuit. And at least in one case, it's pretty straightforward. All right? What's the input resistance of this circuit? By infinity, by inspection, right? It's an open circuit looking into here. So R sub I by inspection is simply equal to infinity. This is a simple one, at least for the input. So that one is easy. You didn't really need Thevenin for that one. You could just tell by inspection. What about the output resistance? That's trickier. If I want to calculate the output resistance, what's the first step I need to do to calculate Thevenin resistance? Because obviously looking at this thing, I've got a dependent source here, right? So what do I do with this dependent source? Well, that's a good question. What technique do you have to use when you're finding Thevenin resistance in circuits with sources? Dependent sources. What do you have to do? What technique do you have to use? Source driving technique, right? We're going to zero out all of the independent sources, and then we're going to connect a voltage or current source across the output, and then calculate it using the source driving technique. So in this case, I'm going to want to calculate R sub O. And so what's the first step to finding R sub O? First, zero out all independent sources. Let's do that. Let's zero that out. What's VGS equal to? 0. What's GM times VGS now equal to? Equal to GM times 0 is equal to 0. What does a 0 value current source look like? Open circuit. Yeah, this is just an open circuit. So as it turns out, is R sub O actually all that difficult to calculate? Actually not at all. Because now R sub O is just equal to, big R sub O is equal to little r sub O in parallel with 10K, which is equal to 9,756 ohms. Now I could have used the source driving technique, and in some problems you'll have to do that. In this particular problem, that dependent source very conveniently disappeared. But you know, you could always use the source driving technique. I could do it this way. Now that I've zeroed out the independent sources, I can use a test source. In this case, let's use a 1 amp test source. Okay? And in this case, we want to find VT, the test value across that test source for our source driving node. And so in this case, 1 amp going in is equal to VT over 10K plus VT over 400K. Or VT is equal to 9,756 volts. And therefore, RO is just equal to VT over 1 amp will be equal to 9,756 ohms. And so I could use the source driving technique. I get the same answer. But in this case, just by inspection, you can tell it's just 2 resistors in parallel. But other problems, you'll have to use the source driving technique because there'll be dependent sources. You can't zero them out. You can't ignore them. So you've got to use nodal analysis and use source driving. All right? Questions about this? All right. A couple other things we want to mention about the small signal model. We are using a very simplified version of the small signal model. So when we go over to this small signal model, we're just doing this. Here's our gate terminal. Here's GM times VGS. Here's my source and bulk terminal. Here's R sub O. Here's the drain. So we're going to use this very simple model. But you know, real MOSFETs are a lot more complex than this. What does any real-world component have? Parasitic capacitance, right? We talked about that. Any conducting materials will have capacitance between them. Well, it turns out that's absolutely the case for a transistor. It turns out that there are actually two capacitances we need to care about very much. There is a gate-to-drain capacitance that we have to concern ourselves with. There's also a gate-to-source capacitance that actually physically exist. And so really, if we wanted a more complete small signal model, we'd have to include those. CGD and CGS. Okay, these capacitances are small. They're typically going to be in the order of femtofarads or attofarads. At high performance, very high frequency designs, these capacitors become an issue. In this class, we're not going to worry about them. In this class, we're going to use the midband assumption. So we're always going to assume that we are operating at frequencies such that capacitors are either so small or so large that they are either open circuits or short circuits. We just ignore them otherwise. So in this case, capacitors will either be large, we talked about this before, such that Z sub C goes to 0, or we'll assume they're very small, in which case Z sub C goes to infinity at all frequencies of interest. So we're going to ignore the effects of these actual physical capacitances. We're going to use the midband assumption. There's a reason for this. If you're going to understand what these capacitors are going to do, you have to understand frequency response. You have to understand poles and zeros. If you have not taken circuits 2 and you don't understand what a pole or a zero is, we can't talk about those capacitors because you will not be able to. You need the math for circuits 2. And this class only requires circuits 1 as prerequisite. So we're going to make it easy. We're going to ignore those capacitors. But clearly, at a high enough frequency, these things will turn into short circuits. And when that happens, this amplifier, this transistor no longer works as an amplifying device. That should be, hopefully, should be obvious to everybody. Once the gate and the source short out, this is not going to be an amplifier anymore. But if you take circuits 2 from Dr. Massengill, you will actually look at the effects of these parasitic capacitances, but not here, not in this class. One other thing you need to know before we close today is there's a name for this model. This model, if you look in the literature, called the hybrid pi model. Hybrid pi, where in the world does that come from? Hybrid pi is a leftover from an analysis technique that was taught 50 years ago, okay? So back when I was taking the class that you're taking now, all right? We learned about two-port theory. And two-port theory was a way of looking at how the characteristics of a circuit from the input port to the output port behaved. And this hybrid pi model, hybrid pi was one of the two-port models. Now nowadays, two-port means nothing to you guys. Network theory is that kind of network theory is no longer taught in engineering courses. But the name has stuck with us. So you'll see it called a hybrid pi model. Don't worry about it. There's your model. But the thing about these two-port models is there are equivalent models you can use. There is, in fact, a model in the textbook. Called the T model. This is an equivalent way to represent the small signal model of a transistor. The T model is a mathematically equivalent way of drawing this small signal model. It is neither better nor worse. For some problems, the T model is easier to use, for some problems. For other circuits, the hybrid pi model is easier to use. Using either one gives you the same answer if you use it correctly. The textbook will occasionally throw a T model at you and will offer you the T model to use. I have no concerns whatsoever if you use the T model instead of hybrid pi. You'll get the same answer if you do it correctly. However, in my lectures, I will always use hybrid pi. But the T model is an equivalent model for you to use if you wish to use it. But if you don't want to ever think about it or mess with it, you can just stick with the hybrid pi model. All right? Okay, so next time we'll briefly talk about the body effect. And then we're going to look at simple amplifier topologies. We're going to look at common source, common drain, common gate. Look at our three basic amplifier topologies. All right, see you guys next time.